Let's review a definition in the area of differential geometry. A topological space M is locally Euclidean of dimension n if every point has a neighborhood that is homeomorphic to an open subset of Rn. Let's unpack that. That means for every point in M, there is an open set U containing P, and an open set in Rn U tilde for which there is a homeomorphism from U to U tilde. In case you don't remember, a homeomorphism is a continuous and bijective function, which inverse is also continuous. The first thing one should try to understand is why this definition makes sense. What idea is it trying to capture? First, one can see that this definition is a generalization of Euclidean space. You can verify that an Euclidean space of dimension n is locally Euclidean of dimension n using the identity as the homeomorphism. But the definition is much more than that. It applies to the general class of topological spaces. But again, what is intended with those neighborhoods U and U tilde and the homomorphism between them? The key idea, as the name implies, is to define what it means for an abstract space, like a topological space, to locally look like the well-known Euclidean space. Globally, the space could be very complicated, but locally is actually very simple. And what does it mean in mathematics when we say something happens locally? It means that it happens in a neighborhood of every point, possibly a very small neighborhood. Then the question is how to express mathematically that a space is locally around a point, like the Euclidean space. So how to mathematically describe that around a point? The space is locally like the Euclidean space. To capture that, we say that every point has a neighborhood around it that looks like a piece of an Euclidean space. In the category of topological spaces, the idea of two spaces looking the same, or being equivalent, is captured by the fact that there is a homeomorphism between them. An homeomorphism, which is an invertible function with both itself and the inverse continuous. Homeomorphisms preserve the topologies and define an equivalence relationship between topological spaces. So, given that every point in M has a neighborhood that is topologically equivalent to an open set in the Euclidean space, we say that M is locally Euclidean.